Yeah, thanks, Steve, and thanks everyone for coming. Let me mute myself on this mic, and I hope people on the online will be able to hear me. If you don't, shout. That's anyway. So today I'm going to be talking to you mostly about YouTube, and basically present a justification for like part of my lab spending more than half of our working time just watching YouTube, and I argue it's a good thing. Okay, right. So what happens? Oh right. Okay. So well, this is basically the broad picture of what my lab works on. Today I'm going to talk about this. You're going to see this blue blurb. On a different day, you might see me talking about vision and language, and like we sort of did some work there, and we also did something in document collection summarization. My take of that is that problems in vision and language is very hard, and it's best right now left to the computer vision experts in this room. On yet another day, you might hear us looking at visualizing academic influences or understanding 100,000 moral dilemmas that are in real life. For example, Josh here is working on that. Today's talk, well, first let me motivate this general problem of why we're interested in YouTube videos, right? On the left was a pop song as of roughly 9 years ago that took the world by storm. And for a long time, YouTube actually has this publicly accessible time series of daily views for each video, or for most videos. And people can see it. You can see that for this song, there is some, it actually wasn't an immediate hit. The popularity rose for a while and then slowly dropped down. And in a steady state, when we had data, it's still a few 100,000 views per day. Okay, here's great. And then on the right is the pop song as of 300 years ago, and it's still getting some constant attention on a daily basis. And this is internet like data, and there might be some data issues there. So the question we ask is, how do attention evolve over time collectively? Like basically, if we are interested in people on the internet as a whole, how do attentions evolve? What drives it? We would like to answer this using publicly available data as well. Basically, when we send a paper to a conference, people say that you haven't considered the user aspect. We're like, we're not YouTube. We're not. So who actually is behind these views? We don't want to know. And we argue there's a lot you could do with just like aggregate time series. So this talk is divided into 3 parts. It will be mostly at the overview level. The first part is what I call measurement, how to describe video popularity. I argue that for problem domains like this, the problems are really not very well carved out at the beginning. So in this, we have a few work about measuring video popularity a few different ways and really understand what problems should be solved and what do the problems look like in this domain. The second part, I will focus on one particular model that we use to model popularity, predict, and sort of explain colloquially what viral video might mean, or try one way to define that more precisely. And the third part is a grab bag of machine learning things that we have done in relation to this. We'll get to that. So these are encoded in a collection of papers. I would specifically like to acknowledge people in and around the lab that I wrote papers with over the years on this topic, actually including Christian sitting over there. So yeah, their specific work will be highlighted as I go on. So this is rather like a 6-year-old picture that we made about what do we mean by popularity or daily or cumulative number of views of videos. We took a sample of 117,000 videos, group them, sort them by the number of views they have at 5 days after upload. So we line up all the videos based on age, and then use the familiar box plot to plot what the views look like. So basically, we group them into 5 percentile bins, from the most popular up here to the least popular here. So videos in the middle are quite similar to each other. They are within 1.3x of views of each other. And then only like the most popular videos have an insane number of views, close to 1 million, so to speak. What is interesting is if we play this plot forward every 5 days until videos are almost 3 years old, that might be too quick for you to see. And here's the overlay of the 780 days on the top and the gray, like 5 days on the bottom. So videos at the middle, like all the way from like the 90th percentile, maybe to the 10th percentile, they gain 2 orders of magnitude in popularity over roughly 2 years. That means videos over here gain from 10 to 1,000 views, video over there gain from 1,000 to like 100,000 views. Rich get richer. But this gain, right? So you say, well, you might say that, well, listen, you've cheated because videos in the same bucket here don't necessarily stay there. That's correct. And here's a view of that. So the x-axis is still the same, popularity percentiles. On the left is most popular. On the left plot, it's news videos at 5 days. On the right are music videos at 5 days. We can see that news videos tend to be on the more popular end, the opposite for music videos. So what happens if we animate these? News and music are the 2 biggest categories in video collections like this, right? So if we play this, well, they don't allow the videos to sync, but you can see that the news videos lose their popularity over time and music videos climb up, like over a long period of time. This is intuitive because news is no longer sort of interesting to watch when it's no longer new, at least most of it, right? But music, you can go back to it time and time again. So in 2015, Hong Lin, the then PhD student, did this work. He basically came up, or we jointly came up with this description called popularity phases over time. So here are 4 example videos. The blue dots are the daily number of views, and the red lines are the current fits. So there is an algorithm behind this to sort of estimate and segment what are the like convex, concave, increasing, decreasing phases. That's less important for this talk, but basically this is a sample about how popularity evolves over a long period of time, here 4 years, right? Some video basically has a spike in popularity and doesn't recover. Some even have a continuation rising dynamic over 2 years in here, and some have like almost a cyclic structure here. So the popularity evolution is actually very complex, right? About this particular one, if you squint at the x-axis, you will know that the peaks happen in the middle of the year, each year. And the subject of that video is how to vent a portable air conditioning. So that corresponds to the northern summer, like now. So here's one stat that sort of motivates why like looking at this might be important to understand popularity. So this plot actually should be read from like the converse, right? So we define dominant decreasing phase, like something like that, a video popularity like this, have a spike and drops off with duration more than 90% of what we were measuring. If we basically plot the fraction of videos that has this pattern, which I argue are mostly uninteresting, is according to the popularity percentile, we can see that most of the unpopular videos have this pattern, 60%. And if we tabulate it against different types of videos, we can see that film and music, the least amount of videos have this pattern, but news, almost 70% of videos have this pattern. So the takeaway here is popularity is inherently unpredictable. You don't like, phases seem to be driven, like they happen suddenly and they seem to be driven by something. And we will get back to this in the middle bucket of the talk. Right? Hold on. So 2 more ways of looking at this popularity data. So one of Siqi Wu's thesis work, some of you might have seen his recent talk or completion talk about this. So he not only looked at individual videos, but also looked at how videos drive views to each other. By one major way of that happening in YouTube is the recommender systems. Basically, we treat the video in the center as the source node and the video being recommended as the target node. And we know that some of these links drive a lot of views. One evidence of this is, here's a picture of 6 Adele songs. Hello was released in late 2015. And at that point in time was the video that gains the most number of views in the first 24 hours of its life. So if we look at the view series of all the other videos, we can see a spike. And this spike, and this is the shape of the recommender network among these 6 songs. We can see spikes not only in songs that Hello is directly recommending, such as Rolling Deep or Someone Like You, but also in songs like Skyfall, where it's not directly pointed to by Hello, but can be indirectly navigated after 2 songs. And this is what the network look like roughly if we roll out from Hello, like just snowballing 2 steps, and we can see many different pop artists and their songs show up. So Siqi collected this 61,000 music videos from 4,000 artists. Level affiliated artists tend to be professionally supported and produced, right? So you might say, what does this mean? Here's a snapshot, and we'll talk about modeling about this again later. So one way we can measure the, say, overall structure of a large directed network is the so-called bow-tie visual metaphor proposed in the early days of the web. They won the test of time award in the web conference because for this. Fairly recently. So the 3 main components graphed here is the largest strongly connected component in the middle, and the in component where you can use the links to navigate to the circle in the middle, but not otherwise. And the out components where you can navigate from the largest strongly connected component, but not going back. So in the early days of the web, these 3 components are roughly the same size, roughly between 20 to 25% of the all nodes. This is the shape, corresponding graph for the Vevo music graph. The strongly connected component is still 23%, but the in component is almost 70%. Our component is very small. You might ask why is this the case, right? So we then rescaled each of these nodes or videos by the average amount of views they have in the period we measured. This becomes the picture. Basically, the strongly connected core now accounts for more than 80% of the views, and the in component only account for 12% of the views. So the popular videos are being recommended a lot more, right, across the spectrum. So this picture actually is not unfamiliar in the social web these days. I think even in 2012, one of my like my group did a measurement on how people talk about news, and the picture is quite similar. The core is much smaller. So what does this mean? We will use this like the network structure for modeling a little later, but we thought people have worked a lot on recommender systems on different, all sorts of different networks. But works that look at, I guess, the overall aggregate network structure induced by recommender systems are not that many. And we can ask what that means. Okay. The third way and last way that we look at this problem domain is not only how many views each video get, but also how much time people spend. So this turns out the aggregate figure is also available from YouTube at that time. Again, this is thesis work. So shown here is the 3 video channels. Each dot is a video. The red channel is the Ellen Show. It's a political talk, like funny talk show produced in America by one of the major TV studios. So you can see that it has lots of views after the first 30 days on average, and people watch on average over 80% of it, which is quite high. In comparison, Kimi, these green dots, is a Korean video blog by a woman blogger talking about how to do cooking, like Asian fusion kind of food. So it has lots of views, but people don't watch as much of it. People finish about 20% of it. There are many reasons for this. One key reason is the length of the video. So in here, Siqi again collected. Siqi collected over 6 million videos in 2016 in order to do this study. And he basically did a density plot. So this density plot is done by binning on video durations, 5,000 bins. And then it's actually, just think of it as a continuous box plot, and these lines correspond to percentile points at each video duration. So overall, the amount of time in seconds people watch increases as the video gets longer. But if we divide this plot, the green plot, by the video duration at that point, the fraction of the video people finish is actually lower as the video gets longer. That's intuitive, right? So how do we quantify like what we call video engagement, basically how much people spend, time people spend? And how do we sort of compare this notion of how engaging video is if they're of somewhat different lengths, right? So what we ended up doing is to basically use a percentile, like create a percentile scale for each video duration. And this basically gives us a number between 0 and 1. And in any video duration, and we can give a video a score. It's basically, relatively speaking, how engaging this video is compared to videos of similar lengths. Here's an example. So here are 2 videos of generally like fighting thing on YouTube. So on the kids doing karate video, it's about, I think, a few minutes. And if we look at the watch time, people watch this long live fighting show more than the kids doing karate. But if we look at the fraction that of the video people finish 80% of the kid doing karate video, but 20% of the live fighting show. But if we look at the relative percentile, both of them are actually like around 90, above the 90 percentile. They are quite engaging compared to videos of the similar length. Right. So you may ask us, why is this like relative engagement metric or percentile metric any good? So we, the blue again is the background. Now just take the normalized view. And then we overlay the number of videos that are arguably of top quality by some external like resources. On the left are music videos that are Vevo. We talked about that in the last work, and also Billboard top songs. They are on the upper envelope of this blue cloud. On the right is the top news channels, 100 top news channels rated by some internet website. And they are also on the upper envelope of this cloud of other videos. What was surprising to us was that CT also measured how stable is the engagement, say percentage of video watched or this relative engagement metric throughout a video's lifetime. They actually don't vary a lot. Only very few of them vary by more than 10% over the entire lifetime. So like within the first few days, you can compute it and it stays there. That's in contrast with the daily view series that we saw a little while ago. So we asked the question, so can we actually predict this watch percentage or engagement metric for each video then? Right? Turns out that we can. We got R2 of 0.77 for watch percentage. The most predictive feature is the reputation of the channel, basically what kind of video the channel makes and how much people engage with it in the past. Not super surprising. What we are pleasantly surprised with was that the second most informative kind of features is free-based categories. So if Google extracts these from the text and video and audio signal out of the YouTube videos and at some point provided it as like an API feed. So we did that. And we tried to understand what kind of topic categories are predictive. So to be honest, for the one question that my grant funding manager keep asking me is, can you predict whether a video will go viral from the audio and video information of the video? The answer is actually no, because once you have behavioral signals, they're always a lot stronger than trying to solve the hard computer vision like computational like audition problem, right? So in here, we can see that generic categories such as music and book are not very predictive. Y-axis is what's called conditional entropy. Lower is better. You can parse the like formula later on. And here are some of the most predictive categories, such as Bollywood and Obama. Why are they different color? Because here's a histogram of video engagement, relative engagement for when the video has this particular feature turned on. As we can see, Bollywood on average is sort of on the low engagement side, but Obama is the opposite. Interesting, this was 2016. All right, so that's basically like our few attempts at understanding problem space. Now let's get to this point about why the popularity is unpredictable and what can we do about it. So here is, I guess, our overarching intuition about why we see popularity like daily view curves like this. They're quite complex. Before us, the view was, okay, predicting popularity from content doesn't work, then I'm just gonna predict it from the history of how popular things are. But things like this, rising and then dropping, there are many changes, it's hard to predict, right? So social platforms like YouTube is not isolated, right? It's being constantly influenced by what else is going on in the world. In particular, say who is talking about this video elsewhere and how much. So the view is the tweeting and sharing activities, let's say, as another time series, continuously influence this observed popularity as an outcome. And the other factors that influence these are, let's say, network effects, word of mouth, inside YouTube recommendation, how highly it's ranked in search and so on, and also system memory. The response for news and music is probably different, and also content quality, virality defined in some way, right? So the video I make is probably a lot less polished than a TED Talk, let alone Gangnam Style and so on, right? So a lot of people here would have heard at least one of my group members talk about self-exciting point processes. So here's another goal. In case it didn't make sense, I hope it will make a little more sense after today. So one mathematical tool that we rely on to describe this kind of phenomena is stochastic point processes. So there are discrete events happening in continuous time. It's a weird sort of a mathematical object. One particular variant is called self-exciting version of this, where the intuition is one event, let's say this blue event happening here triggers future event with this time decaying probability with this, say, memory kernel 5. And then so this blue event triggers this red event and green event as their offsprings, and then they in turn trigger further events. Right? I guess this model is probably more familiar to people now because they're similar to, say, disease transmission. We'll get to that. But basically, let's say the picture high-level picture from last slide translates into, oh, if these are people tweeting, and we put it through a system that have this self-exciting memory kernel, then we get a bunch more like response events. Right? We don't directly use this to model because we don't observe individual viewing events. And even if we do, we don't want to use it when there's millions of them, like the complexity of this like n squared. So what do? We do the following. So on the bottom is the basically same picture and formula where the memory kernel encodes basically content quality, user influence, and memory, and so on. We derive the top formula on the top by taking stochastic expectations of event history up to time t. This is a mouthful to say. What it basically says is there's a, in between 0 and t, there's a random number of random events happening at random times, and we try to like take expectation over that. Detail aside, this equation on the top basically says popularity as a time series is influenced by external stimuli as a time series with a scaling factor that's being learned, and also this essentially convolution term of its own history with the parallel kernel. There's a bunch of parameters in the middle, right? It's a mouthful. So what this means in like machine learning terms is we do a least square fit for each and every video to find about 7 parameters that are interpretable too. And the input data is this red time series of how much people sharing. The green time series is the output of like how many views per day. And the model fitting is this blue curve. As we can see, it's like not a linear relation at all, right? For at least this example. And what does this mean for those of you who have a linear systems background or can remember from your, I guess, undergrad textbook? So this integral equation is actually a linear time invariant system. For these systems, it's interesting to examine what's called the impulse response. Basically, for 1 unit of tweeting or sharing, let's say S of t is the impulse, how many views do we get out over time? So that's the impulse response. What we want to examine, so we simplify this. That's a time, like sort of, it's still a function over time. That's too complicated. If we look at the area under the function, this could be summarized into essentially how many views do I get per tweet. And then we graph this against this mu parameter, basically what is the amplification or like suppression factor for each tweet. We call this 2-dimensional axis the Indo-XO map. I'm going to, and this allows us to put videos on a 2-dimensional map. I like 2D maps, they're like easy to explain. And interpret basically how potentially viral videos can be, or potentially popular videos can be, and compare a bunch of things. So this particular picture are videos from 2 channels, the bigger channel. So more videos with more views are bigger in size, and videos with more shares are darker in color. So we can see that there are a separation between 2 channels. The bigger, the top channel are gaming videos. We click on them, we should be able to see. The bottom channel is a blogger talking about news in Ukraine, like surrounding regions. So the bigger bubbles are sits on top, meaning they have more potential, right? So we can also compare individual videos. For example, this red dot, whitish dot is a video of the ice bucket challenge. Some of you might remember, and it's quite sort of sensitive to promotion, high on the axis, and also has lots of views per tweet. The video, the dark video on the bottom is a mass video talking about how many kinds of infinity there is. Thank you. Yeah, we'll get there. As we can see, it's not as sensitive to promotion. Some of you might resonate with this because if you like it, you know you're not the typical internet user, it's not very broadly appealing, right? Okay, so we can skip over two and say that this kind of map also can help us isolate videos that cannot be promoted. Like if we just take videos, the circle encloses videos where the views to tweet are less than 10 to the minus 3. For example, there's a video blogger talking about how to make pizza by the solution was to order call Domino. It also can identify videos that hasn't been popular but has the potential to do so. There's an example of that. I won't go into it. So basically, the video wasn't very popular, but the metric is very high, and then there were some tweets about it in the next month, and it indeed got like 7 million views last I checked. So that's the second cluster of things. And then I'm going to talk about how we sort of extracted a number of machine learning questions out of this. Some of this you would have heard recently from others as well. Right, so I'm gonna do a quick walkthrough of 3 things. So here is a view of the self-exciting point process again. So on the top are events over time, discrete events over continuous time. On the bottom is what's called a conditional intensity function. Basically, whenever there's an event lined up in time, there's a jump in the event rate over time. You can think of this function as the probability of having one event in infinitesimal time, right? It's a slightly weird object. It's not a PDF. It's what's called a Haza function, if you have heard of that. So it has basically this piecewise continuous, but like jumping structure, right? As with any weird mathematical object, people have tried to whack neural network on it recently, and there has been lots of proposals, right? RNNs, transformer hawks, and RNNs over functionals, and so on. And the intensity function is also not the only representational object we can try to approximate. For example, intensity, what's called compensator, and inter-arrival time distribution, which is a proper distribution, and so on. We asked the question, what is the minimal representation for all of these point processes? So this is work done by Alex Owen during his honors. So the approximation target are this. So we want it to be more general. It doesn't have to be piecewise decreasing. So it's just piecewise any shape functions with jumps, right? The solution are basically in 2 pieces. One is the approximation of continuous function between events. One constraint of this intensity function is that it must be non-negative, otherwise it's not a probability, right? So it requires basically extending the neural network of universal approximation result. We approximate any piecewise continuous function with a sum of basis functions. There's a large menu of basis functions that we can choose from, followed by a transfer function called F plus. Details are less important. The second point is that RNNs are actually universal approximators for dynamical systems. And the output from the RNN, let's say P, will be used to parameterize the sum of basis functions. Putting them together means that RNNs plus the sum of basis functions is actually the most parsimonious and flexible universal approximator for this kind of weird functions. Right? So that's that. The next point, some of you would have may have remembered Chu Kong mentioning this in his recent PhD oral. So basically, what is right? So this self-exciting nature is remotely similar to epidemic processes. So what exactly, is there any connection? We haven't found any in the literature. So here is the broader picture, right? So the simplest epidemic model that you hear about are what's called compartment models. Different for people in the population, they move through different compartments, such as being susceptible, not sick, infected, kind of sick, and recovered. Right. For COVID, it's a bit more complicated. There's a few more states. If we use that compartment analogy, the prompt process over social media is sort of susceptible, not acting on anything, infected, tweeting about a topic, but there is no recovery. Right. If we look at the epidemic model in the prompt process view, it's actually two kind of processes: infection process and recovery process. And they have their own corresponding intensity at the triggering of each event. So we ask the question, what if the recovery events are not observed, right? There can be many different recovery events. So in social media, we don't know whether people can recover from a topic, and in non-lethal epidemics, we often don't know when people recover. They just get better, which is good. So if we marginalize or we sample different sets of recoveries, here are different, essentially, realization of the intensities. If we sample many and just take an average of the infection intensity over a small number of realizations, they don't look much. They're still very boxy. But if we do this enough times, they started to look like something that has a decay, right? And they are that recovery is latent. So the connection is basically, if we marginalize over the recovery events, the intensity, unfortunately, it's in the lower bound of exactly equal sign, is sort of something like the self-exciting process modulated by the population size. This is nice because for social media, because in online information diffusion, you can get into this supercritical scheme where the number of expected events goes to infinity. This is with branching factor larger than 1. A lot of you would have heard about that. But if we have this modulation factor, it guarantees that we will eventually die out, which it should. Right. This one I'm going to talk about briefly. Some of you might still remember Alistair talked about this, his webconf paper this year. So the YouTube recommender system made us think more seriously about networks of time series. Shown here is an example of Wikipedia traffic network among some French political political movement recently. There are 3 components to this problem: time series, network, and dynamic networks. And nobody have quite to put these together, but we argue it's important. So the solution to this has, again, a couple of ingredients. In the time series, Alistair found a recurrent structure with layer decomposition, also with sort of a residual forecast backpass representation works well. On this network component, he does scalable node aggregation, basically plugging. He's able to plug in many graph network structures and these graph attention networks. And then on the dynamic links, he actually has an efficient scheme to on-demand load network data from disk. Otherwise, he wouldn't be able to train things like 360,000 Wikipedia pages. Right? So this is, some of you might still remember the demo. I can show basically a visualization of network of time series and showing the effects of them influencing each other. Try to dig for a different example than the one Alistair showed. So these are Wikipedia pages. So this is, and I was disappointed to find that so there is a lot of views for entertainment related pages, but there is not a lot of views for scientific topics such as CRISPR or black hole or whatnot. Yes, thank you. Yep. So for example, the center like is the Game of Thrones page, and then you can see that it's sort of influenced by Tyrion Flame, Game of Thrones fans tell me what it is. But basically these peaks will correspond to the release of seasons and so on. So that's mostly what I wanted to say. At the end, as entertainment, I wanted to like give you a, I guess, sample of one like improved app that we're building. Here's finally for Sylvie, your basically this is academic influence on your 1 degree sort of network. The blue links are incoming influence as encoded by papers you cite. The red links are outgoing influences encoded by papers that cite yours. And there are 4 different graphs where the outlying nodes are people, venues, institutions, and like just field of study topics. There's a live version where it doesn't animate, but you can navigate and poke around. And this is going to be an archive in the making. So I gathered the authors one, like it's a who is who in, in planning. Yeah, and the gray ones are those who you have co-authored with. And there is one for Steve as backup, but I can send it to you offline. Okay, so okay, there it is. Anyway, I've talked to you about understanding the problem of online collective attention, why it's hard, why it's kind of unpredictable, how to model it, and then basically the machine learning behind this whole thing. Where there are many open questions in this domain, right? So one thing I'm particularly interested in is how do online items compete for attention? Can we model them as a market, or how to, like, I guess this is of like very urgent practical importance. Basically, is there a market mechanism at play, and can we think about good ways to regulate this? And there are many interesting and useful, what I call content verticals in marketing terms, right? So one of our projects, for example, is Cai Yang and others, we're looking at like attention across Twitter and YouTube on political movements. But you could equally examine, for example, how to make good teaching videos. I have my lecture videos on YouTube, and I know that they're hard to watch, and I don't blame anyone. Fuqi, I think just this week said, well, there was a talk about sign languages, and what about like the content segment around those, right? And for example, there are other sections such as games and programming and so on. They all may be interesting to examine. So happy to hear if you have more ideas. So we have a collection of about Twitter activity about any YouTube video over the past, like between 2014 and 2018. And some of those videos we also have their attention history. And I believe no one else has that. So that's, I guess, our claim of we know more about YouTube videos than anybody else outside of Google. Is that, I think I still have time for questions. All right.